So good morning, everybody. Now we are discussing about discrete time Fourier transform, which can be derived the same way that we have derived Fourier transform from Fourier series. So discrete time Fourier series is given by, say, ak summation of ak exponential of j twice pi by n, capital N into n. So this is twice pi by n is the fundamental frequency. Now, when we talk about transform, then what happens, just like the continuous case, we the period, that is the capital N number of points, that tends to infinity in case of discrete time Fourier transform. So in the continuous time case, of course, we have made the capital T, that is the time period, tends to infinity. However, discrete time means basically we don't have a continuous time variable capital T here. The period is expressed as capital N. So if we that tends to infinity and omega 0 tends to 0, the summation becomes an integration, and we can write xn 1 by twice pi, and this integration twice pi x exponential of j omega e to the power j omega n d omega. So, and x j omega becomes n equal to minus infinity 2 plus infinity xn exponential of minus j omega n. In case of discrete time Fourier series, of course, this was not minus infinity to plus infinity. This was up to the period n. So that's why both were periodic. And here basically we extend, when we compute xj omega, we extend the interval from minus infinity, summation interval from minus infinity to plus infinity. That way we can get the continuous omega if we extend. So that can be also thought of from general intuition, that suppose I want to observe a sinusoid, okay, say which is having say 50 hertz. So which 50 hertz means 20 millisecond is its time period. So at least say some zero crossings we have to observe, so that we can say that the time period is 20 millisecond. Now similarly, if for a lower frequency like 1 hertz, we have to observe at least for 1 second to know that actually there is some zero crossing is there. Now for 0.1 hertz, actually we have to wait for further. So we have to observe the signal for a very long time, 0.1 hertz, 10 second, 10 to the power say minus 6 hertz, we have to observe for 10 to the power minus 10 to the power 6 second to observe the zero crossings. Now suppose I want to know that if there is a DC or not. Actually, to know that there is a DC, if it is not given in an analytic form, that xt equal to or xn equal to some constant value or xn equal to constant value, then there is no way that I can know that whether there is a DC signal present or not, because I have to wait for infinite time to know that really there is no zero crossing. Then the signal can, I know that to be sure that that is a DC signal. So therefore, from that intuition, we can say that if we want to make it omega continuous starting from 0 and all other frequencies, so we have to observe the signal. That observation duration has to be from minus infinity to plus infinity. So infinite duration observation is required. So that way, physically, of course.
Sir,
Yes.
sir, in that discrete time Fourier transform, sir, in the expression of xn,
Hmm.
sir, in the integral, sir, you have given a 2 pi, sir. So what does that mean, sir? I mean,
This is
is that
can be minus pi to plus pi, or 0 to twice pi, or twice pi to 4 pi, like that, any twice pi interval, just like for the discrete time Fourier series we have done. Here we are writing that interval of capital N number of points. So here also we are telling, because it is continuous, so therefore we are writing in the twice pi. Okay.
But sir, there the interval is 2 pi. It is periodically 2 pi, but here the
Yeah,
period
it can be 0 to 2 pi, it can be minus pi to pi. So any twice pi of interval.
here we took omega
Sir,
naught
but in
equal to
continuous time,
Omega is
sir, but
continuous. That's why the integration. Omega is continuous, but x j omega is periodic. So x j omega is periodic.
and how do we know that period to be 2 pi?
So that because we have xn here. Okay. So if we this one is xn exponential of minus j omega n. So you can put x say exponential of j omega plus twice pi. Okay. So that will be equal to exponential of that is, we have discussed before that properties of complex sinusoid. Anyway, you can directly write it here. So omega would be here replaced by omega plus twice pi n. Okay, so this is equal to, this magnitude is equal to 1. This is equal to 1 actually. So that way it is becoming periodic. That's the basic property of that discrete time complex exponential. So in the discrete time complex exponential, the periodicity is enforced because of this term, exponential of minus j twice pi by n time. So we can take some examples, some simple example, like xn is equal to, unlike the Fourier transform, here it comes in terms of n, but otherwise Fourier transform, continuous time Fourier transform, we have to evaluate the integration. Discrete time Fourier transform, we have to evaluate the summation. And for discrete Fourier transform, this summation is infinite summations, because all this one is n equal to minus infinity to plus infinity. So therefore this is an infinite summation. So the series need to be identified. That is the trick for evaluating discrete time Fourier transform. Continuous time Fourier transform was easier. You have to evaluate the continuous time integration. So you don't have to remember the series formula. But for discrete time Fourier transform, the series to be identified. So most of the time, the series is identified one of the infinite sum rules, and then that is used for others. So like this case, x exponential of j omega is equal to n equal to minus infinity to plus infinity a to the power n un into exponential of minus j omega n. So that is nothing but because of un, so this is 0 to infinity a exponential of minus j omega whole to the power n, and we have mod a less than n, so therefore this can be readily written 1 by 1 minus a exponential of minus j omega. So similarly, if we have, say, that square function 1 pulse xn equal to 1 for mod n less than equal to n1, 0 for mod n greater than n1. So this is a square pulse. So x exponential of j omega can be readily written as the infinite sum becomes a finite sum from n equal to minus n1 to plus n1. So here we have to apply finite sum rule. So that will be sine omega. That is the sinc function that we have derived earlier for discrete time Fourier series. So same thing is here also. Only thing in the denominator we have here continuous omega. So like that for periodic signal like xn equal to cosine omega naught n, so that can be readily written as sum of 2 exponential plus half exponential minus j omega naught n. Then if we do the summation, j omega naught n plus half exponential of minus j omega naught n into exponential of minus j omega naught n, j omega n, j omega n. So this, of course, this will be, if we combine them, this will be omega naught minus omega, and this is minus of omega naught plus omega. So there will be, therefore, 2 exponentials will come, two delta function, 2 exponentials with omega naught minus omega plus this omega naught plus omega. So therefore, this will be this delta function, but because it is n equal to minus infinity to plus infinity, so those delta function in the Fourier discrete time Fourier series case, we have only 2 delta functions, but here it is minus infinity to plus infinity, so the delta function will be periodic and repeating itself. So whatever be the Fourier transform of the cosine function, that same thing is will be here. Only thing, it will go on repeating at regular interval of twice pi. So this is equal to pi delta minus, if we write only in the principal interval,
So how did we get this pi delta omega minus omega naught minus 2 pi L?
so that is the cosine. When we are doing the cosine transform, this exponential of j omega n is coming. So basically, for cosine transform, we are doing the other way. So that means we are writing this cosine function, these two delta functions as pi delta omega minus omega naught or delta omega plus omega naught in the frequency domain. So that way, or pi will come by 1 by twice pi, but we can write okay. The other way also we can do. That is one way. Most of the cases people do like manipulate this way, or cosine sine functions or cosine function is manipulated by the putting the appropriate delta functions. So now for the sine function it will be minus, that this delta will be minus, and then it is manipulated. The other way is that we can combine, just evaluate one of them. Okay. So it is basically, you can see that at omega equal to omega naught, so this is equal to 1. This is equal to half actually. This is equal to half because half is here. All other places, what will happen? All other places, say half is here. So we have cosine of omega naught minus omega n So both are a periodic function. Okay. So if I sum a periodic function from minus infinity to plus infinity, so that becomes 0, a sinusoidal function. So here also for any periodic function, if we sum, so that will be obviously 0. For one period, any periodic function, if you sum, this is equal to 0. And if you sum for minus infinity to plus infinity, so that means there will be infinite number of periods, but then we are integrating or summing up over a period, so that will always be 0. Only when omega equal to omega 0, at that place this becomes 0 and this is becomes 1. So that way it becomes a delta function. In functional form, therefore, we have to write that delta omega minus omega naught.
Sir,
Yes,
sir, but this pi, how this pi term comes, sir?
pi, because the inverse transform 1 by twice pi is there. Okay.
Okay, sir.
So this one is xj omega is there, cosine j omega n, half of exponential of j omega n. For the inverse transform, we have the 1 by twice pi. So to do that, actually we have defined xj omega equal to pi, this one.
Sir, at omega equal to omega naught, shouldn't this summation become infinity?
Summation become infinity. Actually, pi delta is equal to half into pi delta function. Because actually, as per the definition of this delta function, so that the area of that will be there. Okay, so that's why that pi is coming. So most of the cases actually it is manipulated in this fashion. In this fashion. That x at some exponential j omega is written at two delta functions and then evaluate xn by doing the inverse transform. So that way the periodic functions are handled. Let us say another example. So in this case you can do two way, can evaluate this one. One way is that we know the transform of that un, and then the un minus 2 we can do it. Similarly un minus 6 we can do and then subtract it. That is one way. Another way is that we know that because of this subtraction beyond beyond 5 all values will be 0. So therefore there are 5 un minus 2. So therefore there from n minus 2 there are four delta functions will come including n minus 2. Okay. So this one here, of course, we can write the delta function easily. In the frequency domain, writing the delta functions becomes difficult because this frequency domain delta functions are continuous functions, x exponential of j omega. So that's why that has to be associated with a pi, such that the area becomes unity in the limiting case. But when in discrete case, we can directly write the discrete delta function, which is well defined. So then it is simply you can write exponential of minus 2 j omega plus exponential of minus 3 j omega plus exponential of minus 4 j omega plus exponential of minus 5 j omega. So like that, if we combine, say, two functions like this one, up to the power xn equal to up to the power minus n u minus n minus 1. So x exponential of j omega is equal to, because it is u minus n minus 1, so the unit step is on the negative side. So therefore the summation 0 to infinity will be basically 0. So therefore the summation is minus infinity to minus 1. Up to the power minus n exponential of minus j omega n. So this is, we can make n equal to minus n, or say m equal to minus n, m equal to 1 to infinity, half exponential of j omega equal to the power m. So this is equal to exponential of j omega by 2, 1 by 1 minus half exponential of j omega. So because this summation, infinite summation is from 0 to infinity, basically we have added 1 and then minus 1 is added. So then this 1 by 1 minus half exponential of j omega minus 1. So this gives this one. Similarly, if we do another example, take another example, say xn equal to multiplication of two functions, sine pi n, sorry, pi n by 5 by pi n, which is a sinc function, and another is cosine of 7 pi n by 2. So basically we have two functions x1 and x2n here. So now if we take the Fourier transform of x1n, discrete time Fourier transform, x1 exponential of j omega, we know that this function is a sinc function which will which earlier we have done for that plus minus n1, this plus minus n1, this one, this is in this form. So we can directly write that this one is 1 for mod omega less than pi by 5. Both for Fourier transform and the discrete time Fourier transform, this is an important property which is known as the duality. So that means one pulse or one box function in the time domain will give rise to a sinc function of this form sin pi n by sin pi omega by omega, so that form. And on the other hand, if we have a sinc function in the time domain, so we have a box function in the frequency domain. So for this, of course, for a single box function, of course, there is no Fourier series representation in the discrete domain. So discrete time Fourier series does not exist for a single box function. So we have, of course, discrete time Fourier transform for such cases. Now x2n, we had cosine of this. So x2 exponential of j omega is equal to, it's a cosine function, so therefore there will be two delta function. And 7 pi by 2 is nothing but 3 pi plus pi by 2. So therefore the delta will occur at pi by 2. Because delta occurs periodically in all interval. If we take the principal interval, so minus pi to pi, then there will be two delta functions at pi minus pi by 2 and plus pi by 2. So this way there will be two delta functions for s to j omega.
So can you explain this x to e to the power j omega?
E to the power j omega?
X to e to the power, finding x to e to the power j omega.
Yes, x e to the power j omega. Will not be easy. It will be periodic convolution of x1 exponential of j omega and x2 exponential of j omega. So it will convolute this one, x1 j omega is a box function. So that is convoluted with a delta function. So that's what will happen. So it will be a train of x1 exponential of j omega. So similarly, there will be another train of exponential of j omega corresponding to delta omega plus pi by 2. So therefore, there will be 2 x1 j omega in this minus pi to pi interval, which will be which will occur corresponding to the convolution of the delta functions. So this periodic convolution, of course, will be evaluated only in the principal interval of minus pi to pi. I think before going to this further example, there could be so there can be, say, let us take okay, let us take another type of example, say xn equal to alpha to the power mod n. For stability, we have mod alpha less than 1. So then we have x exponential of j omega would be, say, n equal to minus infinity to plus infinity alpha to the power mod n exponential of minus j omega n. So this one we can now break into two summations. N equal to minus infinity to minus 1 alpha to the power minus n. So on the negative side, this will be alpha to the power minus n exponential of minus j omega n, because then this will be equal to n, which will represent mod n. And for the positive side, of course, mod n becomes n only. So n equal to 0 to infinity alpha to the power n exponential of minus j omega n. So that becomes 1 by 1 minus.
Sir,
Yes.
Sir, in the above step, sir, you have break the summation into two summations.
Yes, negative half and positive half. And so
Sir,
negative half also, because of mod n, so negative half also we have to keep it n. To keep it n, in the negative half we have to add one minus sign. So that's why alpha to the power minus n is equivalent to alpha to the power mod n in the negative half.
okay, sir, understood.
Okay, so this is equivalent to. So next, of course, it is simple. We have to infinite sum and so this can be combined. One minus alpha square by one minus 2 alpha cosine omega plus alpha square. So this becomes exponential of j omega. So like that, I mean, generally for some problems, if it is multiplication, it will be convolution. If it is convolution, that will be multiplication. So that way it can be done. For example, another example can be shown, say, convolution. This is given Hn is equal to up to the power n un. Find yn, find output yn. For input xn equal to n plus 1, 1/4 to the power n un. So we can apply that convolution rule. X exponential of j omega would be 1 by 1 minus 1/4 exponential of minus j omega square, because n plus 1, so this is basically due to the derivative rule. We will write, I think some properties, of course, are very similar, so like the Fourier transform properties. Y exponential, h we have to find. So h exponential of j omega up to the power n un, so that is 1 by 1 minus half exponential of minus j omega. So y exponential j omega is x exponential of j omega multiplied by h exponential of j omega. So that is x is 1 by 1 minus 1/4 exponential of minus j omega whole square into 1 by 1 minus half exponential of minus j omega. Now we have to do partial fraction. So partial fraction, we have three factors: 1 minus 1/4 exponential of j omega, 1 minus half exponential minus j omega, and 1 by 1/4 exponential of j omega square. And if we do that, we will have 2 by 1 minus 1/4 exponential of j omega minus 3 by 1 minus 1/4 exponential of minus j omega square plus 4 by 1 minus half exponential of j omega. So now we can identify it easily. Yn would be two or minus 2. Anyway, we have to check it. Partial fraction is 214 to the power n un minus 3 n plus 1 1/4 to the power n un plus 4 up to the power n un. So this way, I think you can solve DTFT problems. There are two tricks. One is that you have to identify the series, and then you have to remember the sum of the elementary DTFT of some of the elementary functions like delta function, step function, exponential functions, all those functions we need to remember to manipulate it efficiently. Otherwise, every time you have to do that summation and identification of series explicitly. So in the properties, of course, the first most important property in contrast to discrete time Fourier series is that it is periodic in frequency domain. Now then, why do we evaluate DTFT? Because if a signal is sampled in time and we want to know the property of the signal irrespective of its duration, so then we use DTFT. Had it been that we have already sampled the signal and we are not interested the signal with a very long duration or duration of infinite duration, we only interested in say finite number of points. In such cases, we don't do DTFT. We perform discrete Fourier transform, which is nothing but discrete time Fourier series. So essentially, discrete Fourier transform is discrete time Fourier series, where both the interval in time and the frequency are finite, as well as both the time and frequency are discrete. In comparison, discrete time Fourier transform, we have frequency domain continuous. So therefore, though it is periodic, but it is continuous. So therefore, the time domain reaches up to infinity. But because the time domain is a sample domain, so frequency domain becomes periodic. That is due to the basic property of the complex exponential that we have discussed in the first few classes. The other things are simple, all linearity, time shifting. Okay, time shifting is circular shift. Time shifting is a circular shift for DTFS, discrete time Fourier series, but not for DTFT. Now, similarly, another important property would be difference. So difference, we have xn minus xn minus 1. Oh, sorry. It is 1 minus exponential of minus j omega. And then another property would be summation is, of course, is important. So this gives 1 by 1 minus exponential of minus j omega x exponential of j omega, just like the integration in the Fourier transform. Here also the initial value will come into picture, pi into x exponential of j0 k equal to minus infinity to plus infinity delta omega minus twice pi k. This is coming, in case of Fourier transform, we have only this term. Okay. This is coming because of the periodicity. Because of the periodicity, this term is added, that after every period there will be initialization and this value will be added.
Sir? Hello? Sir? Hello?
I think somebody, please mute.
Sir?
Yeah, somebody is talking, please mute. Yeah, you want to say something?
Yes, sir. Sir, here, what is theta?
Theta, there is no theta here, it is 0. I told 0.
Okay. Okay, sir.
Initial value. Okay, exponential of J0. And because of periodicity, in the Fourier transform, we have only x j omega at 0, j omega 0. But in case of DTFT, because DTFT is periodic in frequency, so therefore this initial value will be applied every twice pi interval. So that's why this summation, this is delta omega minus twice pi k and all those things coming. So convolution here actually we should be careful. If it is time domain convolution, then it becomes simple multiplication, that is okay. But if it is multiplication in time domain, this becomes periodic convolution in frequency domain. Because in case of DTFT, frequency domain is periodic. In case of DTFS, actually these two relations, both the cases we have periodic. So that means this was also a circular convolution is represented by a product in the DTFS. So, however, here we don't have to do circular convolution because the time domain in case of DTFT is going from minus infinity to plus infinity. But when we do multiplication and corresponding transformation of DTFT, then it becomes a periodic convolution. Into y exponential of j omega minus theta d theta. So this is periodic convolution. Or circular convolution. So I think with this, let me stop here.